So you probably already know what Datadog is and what Datadog does, but just in case, Datadog is a monitoring platform. We offer monitoring and observability as a service on the various clouds. Some relevant scale numbers. We process tens of trillions of events a day. We have millions of hosts that report to us. We run tens of thousands of hosts on our own infrastructure in dozens of Kubernetes clusters. We run those truly multi-cloud. The company's also fairly large. We've got about 5,000 employees and about 25,000 plus customers. So we run things at substantial scale. And on March 8th, what's appearing here is our official blog post from the incident. But we had a very bad outage on March 8th of this year. We were down completely globally for about 10 hours. We had no services at all running. We did not restore all of our services for the first 24 hours of this outage, and we didn't finish processing backlogs for 48 hours. We were in full incident response for a little over 48 hours. Laurent and I are going to walk you through what happened and how we recovered.
So as Laura said, the outage happened on March 8 this year, but the story begins much earlier. So in 2020, there is a small pull request against systemd that is changing the behavior of systemd network D. So there isn't much detail in the PR, but if you look at the comments, you can see what's going to matter here, right? Is starting with systemd 248, when network D is restarted, routing policy will be flushed because now systemd is supposed to own routing and rules on all the nodes. So it happened on 248, it was backported to 247, but the reason it matters to us is, well, we run Ubuntu, right? We run LTS Ubuntu, so we run 2004, which is based on systemd 245, and more recently we've been moving to 2204, which is running 249. And of course, what matters here is you can tell that the behavior is going to be different because of the change introduced in the middle. So Ubuntu 2204 was released in April 2022, and we started to test it and roll it out at the end of 2022. And by March, about 90% of our fleet had been migrated to 2204. To understand exactly why this matters, we have to explain a little how we do networking at Datadog. So many thanks to Matt from the previous talk who gave you a primer on Kubernetes networking. In our case, what we do is we don't do any kind of overlay. What we do is we try to give all pods an IP from the underlying VPC network, right? So on AWS, pods get an IP from the VPC. The way we do this is we use Cilium as a CNI, and Cilium will allocate additional network interfaces for pods and IPs to these interfaces. Of course, for this to work, we need to specify additional routing rules, right? We need to make sure that traffic from pod will be using the additional interface. And as you can imagine, if suddenly you restart network D, well, you don't have rules anymore, right? And what happens if you don't have these rules anymore? Well, pods don't have network connectivity anymore, nodes don't have network connectivity anymore. So, I mean, we had been testing 2204 for months, right? So why did we only discover this on March 8th? Well, I mean, we run only Kubernetes at Datadog, right? So we never restart systemd, we never restart network D. I mean, we start nodes, the kubelet starts, workloads are deployed, and when we scale down, workloads are removed, nodes are removed. We never restart the nodes, we never restart systemd. Turns out there was a CV for systemd that was announced on March 7th. And well, by default, and we used to run Ubuntu with the default for unattended upgrades for security, well, by default, Ubuntu will download security upgrades daily and will apply them between 6 a.m. and 7 a.m. UTC, right? There's no jitter, there's no randomization, it's between 6 a.m. and, well, there is a small randomization, but it's very small, it's an hour. Well, what matters here is, well, this patch was applied fleet-wide on all our nodes running 2204 between 6 a.m. and 7 a.m. UTC. So consequences. Well, the consequences are slightly different depending on providers. On GCP and Azure, pods and nodes lost connectivity, and you can see this graph here, which I think is pretty impressive. I mean, the number of packets that are sent across our GCP fleet in the U1 is millions of packets per second. And you can see that these millions of packets per second pretty much drop to zero for a few hours. What matters here is nodes lost connectivity, but they kept running, right? So the good thing is, well, we could just restart the nodes. Node would restart, kubelet would restart, Cilium would restart and create network interfaces, and things would get back up. On AWS, things are slightly different. So pods and nodes lost connectivity, but what matters is on AWS, we rely on auto-scaling groups, and auto-scaling groups will apply health checks. So the auto-scaling groups on AWS detected that our nodes were not answering health checks anymore. And so AWS decided that, well, the instances were not healthy, and AWS terminated the instances and replaced them. And you can see here that between 6 a.m. and 8 a.m., about 60% of our nodes in US 1, our biggest AWS region, were terminated. And 60% of our nodes is tens of thousands of nodes. So this is great for stateless services, right? And we have quite a few stateless services because, well, if a node is broken and you replace it, then you're going to get your stateless application back up and everything's going to be okay. However, for performance and cost reasons, we run many of our stateful workloads on local disk. And what happens if you terminate an instance with local disk is you lose data. And of course, this is bad, but it's especially bad for distributed systems if we lose more than 50% of the nodes, because then you lose quorum. And here, we lost quorum for hundreds of the systems. And this meant we had to recover the system manually from backups, which took time. So a very quick summary of the apocalypse, as we call it. So the patch was applied between 6 a.m. and 7 a.m. everywhere. Network-D restarted and flushed IP rules, and pods and nodes lost connectivity. This impacted about 60% of our nodes. On GCP and Azure, nodes kept running. They were broken, but they kept running. On AWS, they were terminated, which impacted very severely the system with local disk. What's interesting there is our initial assessment was very wrong, right? Because stateless systems were back up very fast, AWS seemed okay because we had a web UI, right? On GCP and Azure, we had nothing because web systems were down. So our initial assessment was very wrong. It was that AWS was less impacted than the other regions. It turns out it was actually far more impacted.
All right, so it's March 8th, 2023, and Laurent's been giving you these times in UTC, but I'm going to give them to you in East Coast time because that's where I live and that's where I work. All right, so it's 1:30 in the morning, and like any reasonable SRE, you've just gone to bed because you're a night owl, and your pager goes off. So, okay, that's really annoying. It sucks that you're on call in the middle of the night. Ask me about it later. But, you know, I'll cancel some meetings in the morning. I'll sleep in. It'll be no big deal. So I get up and I go get on work Slack, and I see this. So what you're looking at is our alerting system going from 0% error to 100% error across 3 separate regions. And the very helpful responder who has paged me into this incident saying, I think this might be a Sev1. He's not wrong. Useful information to know about Datadog. What goes down is not typically our alerting system. Our alerting system is where we see the impact of other parts of the pipeline getting delay or going down. So when the alerting system goes down like this, it means that something else is also broken. So yeah, I think this is bad. This is a Sev1. I escalate it to a Sev1. I open a Zoom. I page in my secondary. I start to get some responders involved. And I start to get a status page up, right? Those are the first things we want to do. We want to communicate with customers. We want to get some people involved. We want to make sure that it's at the right severity level. Okay, so a lot of things just happen behind the scenes that we planned ahead for because you don't build an incident response on the fly. First of all, our engineers are responsible for their own systems. Datadog is not a you throw things over the wall to an operations team kind of company. It's a you build it, you run it shop. So everyone is set up to monitor their own systems. Engineers are responsible for their own systems, and they're trained to be on call. That's a lot of what our SRE team does, is set engineers up for success for being on call for their own systems and not monitoring. We also have some last resort monitoring. So the thing that actually paged in our responder doesn't run on Datadog infrastructure. It will work even if Datadog infrastructure is completely down. But most of our monitoring does run on Datadog infrastructure. We have an incident app, and we will find that the incident app is quite useful for coordinating. Conveniently, the incident app is stateless, so it was still working on AWS for most of this incident. But we use it for a number of things, especially coordinating these kinds of problems. And useful in this Datadog incident app is that when you open a high severity incident, it automatically pages our rotation for high severity incident command. It's a rotation of senior engineers. There's about 30 people in it these days. That wasn't always the case, but that's how many people are there now and were there in March. And those are just people who are good at incident command and coordination, in theory. And then finally, we are very fortunate that we have executives on call. We actually have VPs on call, and when we escalate an incident to Sev1, we page in those VPs as well. So within about 10 minutes of this incident being opened, I had a VP in the room to help write customer-facing messaging and to help set business priorities around all of these kinds of issues. But what do we do? Because this cannot happen. Datadog runs totally separated infrastructure. Nothing is global. We're not running a global network. We're not running a global configuration system. We don't have a global control plane. We don't do immediate global rollouts. We certainly wouldn't do them at 1:30 in the morning. We do gradual rollouts. So this can't happen. We cannot possibly go down globally. But we obviously just did. So now what? Something must have broken it. We do have a configuration system. It's not actually a shared configuration, but maybe someone had done something in a shared way. We paged the team that runs that configuration system. We also paged the last team to make a change to it, which happened to be our web UI team. Since the web was down in GCP, that seemed like maybe a possibility. When everything is down, it's usually the network. It's often DNS. Let's page the networking team. And also, right, we can't seem to SSH into our Kubernetes nodes to get even baseline telemetry there. Let's page the compute team, right? And I want to point out, we don't know what's going on. It's 1:32 in the morning. We know that we're globally down. We don't have any idea what's going on. And it's really valuable to just know that you can pull in the people who might be experts and ask them to do their best. This incident was really, really extreme, right? Normally you would have some idea what's going wrong. You can at least use the services that are returning some kind of telemetry. Our telemetry's down. We can't get to our nodes to look at our telemetry more directly. So we're about an hour in, right? Various people have joined the response, and we finally get to understand that something has happened to our Kubernetes nodes. It takes us another 45 minutes or an hour to work out that it's no longer happening. And now we get to fix it, right? We still don't know what's happened, but we need to recover, and we need to do it at scale.
So, as I was explaining before, the behavior was slightly different between GCP and AWS, and our initial assessment was that AWS was less impacted, and also given the timing, most people were getting up in Europe, so it was easier to focus on Europe at the time. So to understand the steps we had to take to recover, you have to understand how we run Kubernetes. So we run Kubernetes ourselves, and the way we run it is we run actually different flavors of clusters, right? So we have parent clusters which run on VMs, so very standard Kubernetes deployments, and all our child clusters where we run our workloads are actually have that control plane running as workloads in pods in the parent cluster. And this meant that in terms of recovery, as Laura was saying, when we paged the compute team, they had no idea what was happening, and the first thing they did is try to kubectl, try to SSH to nodes, and all this was not working. Suddenly someone realized that, rebooting nodes fixed them, so, first we had to recover the parent control plane, right? So we had visibility on what the parent was doing and how the child cluster control plane were doing. So first, fix the parents. Then we fix the nodes in the parent, where we run the control planes for child clusters, and now we can know the extent of the damage because now we have a view of the child workload, the child node, right? We know that most nodes on this cluster are now down, and we can do step 3, which is restart these nodes. Of course, you can imagine what it means in terms of scale for Datadog, right? So we started by recovering the parent clusters, and as you can see, it's only a few nodes, right? And you can guess from the shape of this graph that the other ones are going to be bigger. And after we restarted the parent control plane and we started to understand what was happening, we started to reboot servers hosting the parent nodes and the control plane for child clusters. This is the second step. And finally, in this step, it really took hours, we had to recover clusters themselves, or restart the nodes hosting the workloads. So at that point, after a few hours in the incident, we had visibility in the clusters, and most nodes were back up. The problem is, during the first few hours of the incident, we had accumulated a lot of backlog, and API calls from users were retrying and sending us more data. So we had to scale up. We had to create many new nodes to recover. The problem is, well, cloud is elastic, but we wanted a lot more new nodes, right? Many new nodes. And we started hitting interesting limits. So the first one is we discovered a limit we had never heard about on GCP, which was the maximum number of instances in a parent group. So we're very aware that there's a maximum number of instances you can run in a project, and we have warnings and quota for this limit. But this one we didn't know about, and we discovered it during the incident. Luckily, we have a very strong relationship with providers, and this limit was raised pretty fast, but still it's interesting to discover this during an incident. Then, I mean, of course, there's no magic, right? Our Kubernetes nodes run in subnets, and the problem is these subnets have a finite size. And we tend to target, depending on cluster, but we tend to target 50% utilization for these subnets. But the problem is when you want to scale by more than twice, well, you hit limits. And you can see here that we hit, for 3 clusters, we hit limit pretty fast where we created many new nodes, but we couldn't create any more nodes because we were out of IP addresses in these subnets. So in terms of timeline, this is a recovery for the EU1 region. You can see that we have a very fast scale up at the beginning of the afternoon, where suddenly we hit the limit of the parent group. Then it's raised because we've started with Google and we hit the new limit with the subnets. And after a few more hours, so by, I think, midnight UTC, everything was okay, and things are going back down because we've started to process backlog and things are starting to recover. So AWS, as you remember, was actually far worse, right? Because we had lost data. And one of the challenges we have with AWS is that AWS is actually much bigger. So, I mean, same thing, right? We went parent cluster and child cluster, so the first thing we had to do is recover parent clusters and control planes. The thing is, our control planes actually we run them in stateless mode, right? The only thing that's stateful in a control plane for Kubernetes is etcd, and we actually run etcd with remote EBS disks, which means getting new nodes and reattaching the disk just fixed things. It still took a while. I mean, you can see that most clusters recovered in about 2 hours. There's an outlier that is at 3 hours. And the reason it took a bit longer than expected is because, well, we were asking a lot from AWS. And when I say we were asking a lot, I mean, this is the number of instances AWS was trying to run, new instances AWS was trying to run on our behalf. And this is thousands of instances that were created in a matter of minutes. And of course, it means we were hitting rate limits and had to retry, and that's why getting new nodes was taking time. This is even more complicated and worse in the context of Kubernetes, because when you get a new node in Kubernetes, there are a lot of different steps you have to go through. The first thing is, well, you notice when you ask for a new node, its state is, well, it's not started, right? We've asked the API, can you create a node? And we have to wait for AWS to create the node. But when the node is running, it's not over yet, right? Because we have many more things to do. The first thing, well, we need this node to join the cluster. And for a node to join a cluster, well, we need to get a certificate so the node can connect to the API server and present itself as a new node for the cluster. The way we do this at Datadog is we use Vault to issue these certificates. So nodes will ask Vault for a certificate and present node credentials. Vault will validate these credentials against AWS, and if the credentials are valid, issue a certificate, and then the node will register with the API server. We're not done yet because, as I was explaining before, the way we do networking is we use Helium, and we have to allocate an additional network interface for pods, right? And this means there's a phase where nodes are not ready because we haven't allocated a network interface and we don't have IPs yet, so we can't get pods IP, so of course the node is not ready yet. When all this is done, we're ready and we can now schedule workloads. The reason I mention all this is because we're heavily dependent on APIs from providers to achieve these steps, right? First, we have to run instances, then we have to describe them, and finally, we have to create a network interface and allocate IPs. So if we get back to the recovery of the incident, this is a number of nodes that were not ready across our clusters over time, right? And you can see that, of course, we have 2 periods. Yeah, we have the morning and the afternoon, and we're going to talk about the different part of it. So first, we're going to talk about the blue and the dark purple parts there in the graph in the morning, nodes that were not started and unregistered. So the reason we had quite a few nodes that were in not started state is because, well, we were asking AWS to create tens of thousands of instances on our behalf. And of course, AWS had to create them, which took some time and Node-REMIN started for a while. We also had quite a few nodes that were in unregistered state because Vault could not issue certificates for them because, well, it was also rate limited by the AWS API when it was validated credentials. We also have this light purple, very big chunk here, right? That was very weird for us for some time. And so let's focus on these nodes. It turns out it was only a problem for 3 clusters, the 3 metric clusters, which are the biggest cluster we have in this region at Datadog. It's thousands of nodes. And we noted that these clusters had thousands of nodes that were not ready. And so we looked into it. It was very interesting. And the reason these nodes were not ready is because they couldn't get network interfaces. So to understand this, we started looking at CloudWatch and to see if we could see if we were rate limited by AWS. And it turns out, I mean, this graph is showing absolute numbers, but about 99.9% of the calls to the Create Network Interface API were rate limited by AWS. And because these calls were rate limited, we couldn't get network interfaces. And because nodes couldn't get ready, the cluster autoscaler which we used to create new nodes was adding new nodes. In addition, we discovered afterwards a bug in the Cinnamon operator where there was aggressive retries and exponential backoffs were not working. So we had new nodes failing to create network interfaces and retrying very fast and very aggressively, making things worse over time. So to solve this, we had to do 2 things. We had to remove all these unready nodes, right? And to start to decrease the pressure on the API. And also, we managed to get AWS to raise these APIs for us, the rate limits, so we had more headroom. And we recovered early in the afternoon. After this, when things started to be stable at the beginning of the afternoon in the EU, around 2 p.m., we started hitting a new kind of problem. So you can see here the 2 blocks of unregistered nodes in the afternoon. And if we zoom in on them, we can see that it was actually a problem for several clusters. And this one was actually the worst for us because the number is lower, but the impact was actually much worse because from around 2:30, we started, we have many automated autoscaler that are actually adding nodes when we have things to process. And of course, we had a lot of things to process. And these new nodes were arriving pretty fast and asking to register with the cluster. And it turns out we actually put Vault in a state where it couldn't work anymore. It was extremely unstable because it was receiving so many requests and it was getting rate limited by AWS so much that it couldn't do anything, right? And this lasted for hours because we had to implement rate limit at the Vault level to make sure that we can only admit part of the request and actually admit new nodes to cluster. Once Vault got stable at the end of the afternoon, suddenly things were okay and we could start recovery itself. This is the summary of the recovery for US1. You can see here that the view of pending pods, so pod that we want to be running but we can't run yet. So in the morning, there's the initial impact because the nodes were deleted. Then we have the big chunk where the matrix cluster can't get ready because we can't get network interfaces. And then you have the issue with Vault where nodes can connect to clusters. And now that we have a good idea, let's see how we did on the human side of things.
Yeah, so I always think it's really interesting when we're talking about incidents like this. Folks, two people stand up here on a stage and say, we a bunch. Let me assure you, we is a much, much larger number than 2 people. So you probably didn't notice this. This is the same initial Slack screenshot that I showed you before. That's 500 people on a Zoom call. Now, they weren't all on the Zoom call at once, let me assure you. That Zoom call was open for about 14 hours. Zoom has a fascinating feature where if you end a call and if you leave a call and you were the person to start it, or you're currently the host, it's very tempting to end the call for everyone. So we had to open, I think, 3 or 4 Zoom calls during the incident as the main Zoom. But this one was open for about 14 hours. And eventually, at various points, 493 different people joined it. This is not the only Zoom call for the incident. Not every engineer working on this incident joined that Zoom call. Again, they weren't all there at once. I don't think we ever had more than about 30 people in the room at once. But we had more than 500 engineers working on this incident. So how do you get to 500 engineers and how do you organize them? we have a major incident commander rotation, right? That's a senior engineer who's responsible for commanding those incidents. We also have engineers who are responsible for running their own systems. And culturally and also sort of practically, those folks are starting to come online, especially in the EU, but some of them just don't have great work-life balance, or they're on the West Coast, so it's like only 10 o'clock and they think it's totally reasonable to be on Slack at that time for whatever reason. And they see something's really wrong, right? Something's going on, it's a big deal, the website isn't working, and they join the incident response. They want to help out. And they know how to integrate themselves into an existing incident response. That's two things, right? They understand that the structure is that there's an incident commander who's in charge as things go on. And also, they know how to open work streams. So work streams are just a feature of our incident app, but they're also something that we think about fairly culturally. Each team or major subproblem for the response, you just open a work stream. And those work streams have a lead who sort of functions as a local incident commander. They know how to keep up with the larger response. They know how to kick problems up to the larger level incident responder. And then a work stream is just this group of people is working on this problem, or this group of people is recovering the services for this team. The Datadog incident app supports these both by designating a work stream lead and by opening a Slack channel for every work stream that's opened, which means that we can also see roughly how many work streams were opened for this incident by 500 responders. I'll save you counting. There are about 70 on there. So those are some things about organizing a large-scale response that went really well, right? People joined, people knew how to integrate into that response. We had the training in place and a skeleton for the response structure. So it's all sunshine and roses, right? Okay, so number one, as people join, you've got a lot of people joining an incident at once. They want to know what to do, they want to know how to get involved, and they want to know what theories we're looking at, what they shouldn't be doing, right? For example, while our compute team were fixing our parent clusters, we really didn't want people to restart the non-parent clusters. That wasn't going to go well for anyone. So you want to be able to communicate all of those things. And I don't know about you, but I reach for a Google Doc when I've got sort of a rapidly changing situation that I want to share with a lot of people. It turns out that there's some challenges here. This is a documented limit in Google Docs. A maximum of 100 people can have the document open for editing at the same time, or a maximum of 100 tabs. 500 responders, 100 tabs, that seems to be a problem. Pretty simple fix. You just make sure that the main link that you share with people is in view mode, not in edit mode. But you have to remember to do that. Second, how do people find that this is the document that they should go to? How do you tell them as they join? We pinned it in Slack. We also shared it directly with people, right? Some really basic stuff, just here's where the document is. Mostly what we found is that as work streams really started to get spun up, people started to share the context there, both the document and then what your local context was. And a final question about a Google document is, who's the audience for this? Remember, it's not just engineers being impacted by this incident. People are filing support tickets. People are reaching out to their customer support reps. People want to know what's going on. And so folks who are very much not engineers are opening this troubleshooting document, and they're not sure what they can communicate with customers. A lot of this isn't written in language that's appropriate for communication with customers or that makes sense to salespeople or to support people. And again, the solution is just build another document that's for support, that's got approved messaging, that has appropriate messaging and context for people in support about what's going on and what we know so far. Again, more than 70 Slack channels opened, right? You cannot possibly read every Slack channel live as the incident commander. So some solutions of this are built in by the incident app. Each workstream has a designated lead, and those designated leads, in theory, know to surface problems to the incident commander, but there's variability in exactly how they do that and exactly how trained they are on that, so we'll come back to that in a little bit. But also, the incident app will let you ask every workstream lead for an update in a relatively central way, which is pretty handy if you need updates from 70 people. On the other hand, if you need to just get everyone's attention, if you need to say, please stop making new nodes while we fix Vault, for example, that's pretty hard to do. It's really hard to just get people in 70 different Slack channels who aren't paying attention to the main channel, which is by design, right? They want to fix their own problems. They shouldn't be paying attention to what's happening to everyone else most of the time. How do you get their attention? We didn't have anything really built in for this, for sort of immediate attention. We just made a Slack group, and we added workstream leads to them. And we just had some people on the response whose job it was to post in a lot of channels, to go bother people, especially when, for example, we'd asked for an update and didn't get it. We wanted to clarify that what we wanted was the customer impact, not where you're at in terms of service repair, things along those lines. Sometimes the right solution is to just throw a warm body at a problem. I also want to talk a little bit about human factors. So Laurent showed this chart earlier of our restarts on GCP. Some things that are really interesting here, right? Each color is a different cluster. You might notice that some clusters got restarted a lot faster than others. It's just who's restarting them. Some folks are much more comfortable with a very YOLO approach, and some folks wanted to take it real slow and steady. And it's actually quite possible to say who restarted which clusters based on what speed they went at. A second thing that's really interesting here and that is very relevant to incident coordination as a whole, those blue clusters are actually our metrics clusters. Those are the ones where we run the metrics pipeline, which is kind of like an important part of the system, kind of an important product at Datadog. So why did we take the longest to restart that one? And it's a couple of reasons. Number one, the metrics team is largely not based in the EU. They're one of our teams that's mostly in the US. And as a result, fewer of them were online at the time that this incident was happening, and there were just fewer of them to advocate for their needs. And there's just a lot going on. It's just too hard to keep track of everything all at once. The second reason is just cultural. Our metrics team tend to be a little bit less active about advocating for their needs, a little bit less loud about what's going on and how much they need and that they need support from other teams. And that sort of culturally filtered into the incident as somebody in metrics said sort of quietly in one place that maybe they were still having problems, but then when nobody came back to them and said, yes, we agree, we need to get that fixed, they didn't get louder, whereas folks on other teams did get louder when that happened. And that's just a human problem, right? So in summary, right, I want people to note that we had some pieces already in place about how to build a large-scale incident response, but if we had tried to practice a response at this scale ahead of this incident, it wouldn't have helped, right? What we actually needed live and what we would have discovered in a tabletop, I think are incredibly different things. And it's really valuable just to have responders who are comfortable with the idea that you might need to build incident organization live. You might need to figure out what tools you need and how you want to go about responding in the moment, just as you want responders and SREs who are capable of building scripts to solve their problems live as it happens. Some things that were really interesting about our major incident response rotation, because that's a relatively large rotation, we were able to have 3 people from it working on the incident basically at all times. We wound up with 1 person who was in overall incident command and 1 person running as communications lead. And then 1 person whose job was basically just to go be a helpful senior engineer for any work stream that was particularly stuck or blocking other people or needed to give a better report about what was going on. So just, there's a trouble spot over there. Can you go figure out what's happening? It was really, really useful to have someone we could use for that without having their incident commander sort of stop paying attention to the overall incident command. Some people we often don't talk about as SREs during an outage like this, but I really want to call out our support team. This is the number of customer support tickets they received. It's normalized so that 1 on the graph is their regular workload. You notice that there is a 25 to 35x increase in their number of tickets during this incident. Every single one of those tickets got an individual response from a human being. That's really important to us as a company. When people take the time to reach out to us, it's really important to us that we actually give you the benefit of a human response. So our support team answered all of those tickets with actual humans. I've also mentioned a couple of times that execs were involved in this call, and people love to ask what were executives doing, like threatening people with being fired or any of those kinds of things. No, that is not in fact what our execs were doing. The most important thing that our execs were doing, our engineering VPs were doing during this actual incident was looking calm, making sure that everyone knew that it was going to be okay. The second big thing that they did was talk to customers, right? They composed our messaging for customers on the status page, and they took customer calls. They just got on the phone with big customers and reassured them that, yes, this was a very big deal to us and we were working on it. A couple of other really important things that they did, they approved expenses, right? People were working outside of their normal hours. People were staying in the office a little bit later than usual. They let people know that it was fine to expense dinner. It was completely reasonable to expense a cab home. Yes, please do those things. And they reminded people to rest and hand off. And in fact, speaking of handoffs, we don't really have the tooling to track this, so I can't guarantee it, but I did do some asking around at the company, and I cannot find a single engineer who was actively in this response. Remember, we had full-scale incident response stood up for 48 hours. No single engineer was on continuously for more than 8 hours. Some of that's about having a very deep bench of engineers, right? The you build it, you run it means that we have a lot of people we can pull in. But some of that also means that execs were encouraging people to rest, and it means that there was some leading by example. So remember that I got paged for this initially at about 1:20 in the morning. By around 5:30, right, we've understood that it's a Kubernetes problem. We have a mitigation for GCP. And we know that the different cloud providers are in two really different states, right? We know that there's something going on in AWS still. We haven't quite figured out what's going on. We know that GCP is on the road to recovery. And so we wanted to split the response into two different streams, and this was suggested to me, and I totally agreed that it was the right thing to do, and I contemplated doing it, and genuinely my response was to want to burst into tears. I am just overwhelmed, and I know that I'm gonna start dropping balls, right? I haven't slept. I've been spinning up this enormous incident response with the global outage, where we don't even know what's going on for a lot of it, for several hours. There is no need to be a hero. You do not have to continue pushing yourself past the point of what you can realistically do. I hand it off, right? And you should always remember that that's an option. And in fact, if you do that, you can then stand in front of a really big room full of people and talk about what a great hero you were for handing off. And that's the first about 12 hours of this outage, right? That's how we got our infrastructure back. Once the infrastructure is back up and running, we have to recover all of the services that run on top of that stack. You're probably unsurprised to hear that there's some surprising interdependencies in systems that don't turn off or on very gracefully. Teams had to recover from backups. They had to fast forward through backlogs. They had to scale up to process those backlogs. They had to find solutions for problems with data completeness. And they still had to do a lot of that with limited or no visibility into their products. As with most complex systems, it is very hard to turn off and back on again. So, things we learned from this outage. This is my big takeaway. Common infrastructure, if you run the same distribution of Linux everywhere, you have a global lever somewhere. Even when nothing is global, you have a global outage vector. And then the second one, the big one for me, our coordination processes work. There's always room for improvement, but the basic structure of incident management, you have an incident commander, you have responder, people know how to get into those roles, that's enough. Making them work, right, is a process of trust, it's blamelessness, it's practice, it's being willing to build ad hoc process as the incident goes along.
And of course, I mean, we run at significant scale, but we are quite often reminded that this scale is significant, and when you have to do a very fast scale up, or when something very bad happens, you actually will put so much stress on the providers you depend upon that sometimes things are not going to recover as fast as you imagine. Also, as Laura was saying, I mean, we don't often stop everything down and start everything up again, and so we discovered very interesting dependencies between our services. Some of them came as a surprise to everybody, and we removed them since, but it was definitely very interesting. Something we wanted to say too is we have a very strong relationship with the partners we work with, and we wanted really to thank them because we reached out to them and they helped. I mean, the CDM team immediately found a way to make sure that IP rules wouldn't be deleted by systemd by changing the way they inserted them. And cloud providers like AWS and GCP went out of their ways to raise APIs that were not even publicly documented. Thanks to all of you for listening to us. We weren't able to dive into details in 40 minutes, but we have very detailed blog posts about what happened. Also, if you're interested in solving these kind of weird issues, well, I hope we don't have this too often, but we're still hiring. And we're at time, but we'll be around for questions, and you can ping us on Slack, of course. Thank you.
Thank you.